So for the next 4 classes, the last 4 classes of the semester, we're going to be talking, actually the next 3 classes plus 1 guest lecture. We're going to be talking about Markov decision processes and try to introduce the notion of reinforcement learning so we can actually quickly introduce how RL systems are trained using neural networks. Now, we have a class today. There's no class on Wednesday, obviously. On next Monday, Ryan will be conducting the class instead of me because I'm going to be away in Iceland next week, at least through Wednesday. No, this is just a different conference. Actually, it's not even because of me. My wife Rita has been introduced to some women world leaders conference, and she's going to be sitting next to Nicola Sturgeon and people like that, I guess. And I just get to tag along as the husband. But Northern Lights, who can skip the chance, right? And on Wednesday, we have a guest lecture by Graham Newbig. And Graham is probably one of the top half dozen people in the world on the use of neural networks for language modeling or natural language processing. So that must be a fun lecture. Right now, here's where we are, right? I like to draw this curve when I begin talking about Markov decision processes and everything that you know about neural networks in general. And this is, the understandability versus time curve. And that's where you are in the scheme of things. And on today's lecture, by slide 10 is where you're going to get to that point, which is where you cross the 0 point, right? And then afterwards, it's going to be all the way down, and it's a pretty steep curve. But I'll try to keep it clear at least. And I'm hoping you guys will sort of engage. I'll ask you questions, and let's try to make sure we understand what we are talking about. This stuff is really fun if we get it right. So I'll start off with a little story. I've done this thing before. You have Flider the spider and Spy the fly are in a room. The room is a perfect cube. And the fly is sitting in one corner of this room. The spider has a strange habit. He only walks along edges. He does not cross diagonally across any surface. It takes him 1 minute to go from one corner of the room to another corner. Anytime she arrives at a corner, she randomly chooses one of the 3 edges to follow. Right? You get the setting. And so, what is the life expectancy of Spy the fly? How would you go about solving this? Anyone?
The simulation.
You can do this with math, right? How would you do this mathematically? So this is a fairly straightforward question, nothing particularly complicated about it. Let's say, so first step, let me assume that let me assign a life expectancy to the fly when the spider is at each of the 8 corners. So there are 8 corners. The life expectancy of the fly when the spider is out here is obviously 0, right? And so I have T1. These are the 8 corners. I've numbered the corners, right? And the life expectancy of the fly when the spider is at corner 1 is T1. Over here, it's T2, it's T3, T4, T5, T6, T7, and T8 is 0. Once I state this, then you can actually find the relationship between the 2, right? Over here, what is the probability that the spider is going to go along this edge? 1/3, right? Along this edge is also 1/3. Along this edge is also 1/3, right? So I can write the formulae out, right? Out here, if the spider is out here, let's say the life expectancy is T1, then the T1 is 1/3. With probability 1/3, it is the time taken to go here plus the life expectancy from here, right? With probability 1/3 is the time taken to go from here to here plus the life expectancy from here. And with probability 1/3 is the time taken to come from here to here plus the life expectancy from here. So I can say T1 equals 1/3 of 1 plus T2 plus 1/3 of 1 plus T3 plus 1/3 of 1 plus T4. Right? Everybody see what I'm doing out here? And I can write the same for each of these 8 corners, except for T8, it's 0. And so now I have 8 equations, 8 unknowns. These are linear equations I can solve. I can compute the life expectancy of the fly, right? Very easy. This is the so-called Bellman equation. We will encounter it again and again. Just hold this and or just keep this concept in mind. Now, the spider really is, this whole thing is what we will call a Markov chain. Why do I call it a Markov chain? There are 8 possible states for the spider to be in, 8 corners, right? And once the spider is at any corner, what the spider will do at that corner doesn't depend on how the spider actually arrived at that corner. So a Markov process is one where the future doesn't depend on the past. It only depends on where you are. It's a perfect metaphor for life. It doesn't matter how you got here. It only matters where you are. Right? That's a Markov process. And so here, in the case of the spider, again, it doesn't matter how the spider got to a corner. It only matters where the spider is. And that's why we can write these equations. We're not looking at the referring to the past, right? And if the room has many corners, like a Fuller's dome, how would we do this? Same thing. I just have a great many more equations. But otherwise, the problem is exactly the same, right? Everybody comfortable with this? So let's change gears a bit and let's get into the actual topic of the problem. Playing games. Way back when, 1997, Garry Kasparov was the world chess champion. He was the world chess champion for a very long time. And probably the greatest person ever to play chess. But IBM came up with a computer called Deep Blue, which beat Garry Kasparov in a game of chess. It was the first time a computer had beaten a grandmaster in a game of chess. Now, anybody know where the first computer program that beat this was the first time a computer had beaten a world champion in chess. But does anybody know where the first computer that would beat a grandmaster in chess was built? Computer game? CMU, right in Wien Hall. It was a PhD thesis of a guy called Thomas Anantharaman, who wasn't even really interested in chess. He was working on the design of processors for dynamic programming. And so one of the dynamic programming algorithms is the Viterbi algorithm, and they wanted a really challenging application for this processor. And a really challenging application was, hey, let's try to beat beat people at chess. And so they went about building this chess game, and his PhD thesis was literally having his chess game beat a grandmaster. That's a pretty good PhD thesis. Then he went to IBM, and so Deep Blue was the continuation of his PhD work. And of course, IBM took the credit for it, right? Yeah.
Does it matter who plays first?
Nope.
But I assume that the person who plays first has an edge, or like the computer.
This computer, it doesn't matter. These things just win. We will see exactly how, right? And in the case of chess, we have no proof one way or the other that there's a distinct advantage for playing white or playing black.
What if two computers play against each other? Would that be, is there a probability difference between who will win?
Let's take a look. Okay, so now, but continuing on. AlphaGo. Once we sort of conquered chess, the pinnacle of AI was considered to be Go. Now, in chess, the number of possible states, valid states in the game is 10 raised to 120. Now, what this means is that if you look at every possible chess game ever played in the history of mankind between any two people, and you aggregate all of the board states that they all have achieved over the history of mankind, And then you ran, that number is less than 1 trillionth or 1 trillionth of 1 trillionth of 1 trillionth of 1 trillionth of the possible number of states in the game of chess. In other words, if you randomly arranged coins on the board, the probability that that arrangement has never been seen before is almost 1. Right? That's how many possible options there are. And computers manage to beat grandmasters at it. But then let's move up to Go. In Go, the number of possible states is 10 raised to 160, which is 10 raised to 40 more than chess. So it was assumed that computers are never going to beat humans at Go because it requires real intelligence. And then, of course, AlphaGo these days AlphaZero can begin to learn Go from scratch, and a couple of hours later it can beat the world champion, right? So we mastered this as well. Now, suppose I asked you to write a program to beat Magnus Carlsen. Let's go back 20, 30 years. And I want you to write a program to beat Magnus Carlsen. How are you going to do it? Magnus Carlsen, of course, is the current world champion, right? How are you going to do it? Clearly, you cannot just do it by making up a table of rules. You can't say, if this is the position, make this move, because as we saw, there are 10 raised to 120 possible positions. You're not going to be able to make a move rule for every one of these, right? You can't come up, you'd like to have some general principles. If the move has some, the position has something of some characteristic of this kind, you probably want to make these moves, but who's going to tabulate those moves? Those moves too are going to be way too many in number, right? So how do humans do it? We do it by playing or observing, except the probability problem is that the tree of possible moves is exponentially large. You're never going to just memorize things. What we do is we sort of play the games and somehow we come up with generic principles that enable us to play better in the next move. But here's the great thing. The difference between you and a chess champion is almost world champion chess player is probably not your IQ at all. You guys, especially at CMU, I'd say the average CMU student has a higher IQ than the average world chess champion. So, you mind shutting the laptop?
I'm just putting your notes.
Okay, fine. So, the difference is the average world chess champion has played many games, but then more than that, they have studied many games, and they've watched many games, and they've memorized them all. They remember. So you can actually grab Garry Kasparov and say, can you how did you play the game in whatever Helsinki 1973? And the guy's going to recite the entire game for you. I played KP1, my opponent played KP2, blah 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 blah, and he's going to do the whole thing. I know this to be true because I have actually had acquaintances and friends who were ELO-rated chess champions who would do just this. They would recall games in their entirety played 20 years ago. So it basically means that a lot of what chess champions do is based on experience and memory. So, and from that, they're able to generalize to general principles. But then if you wanted to write a program to do this, and how would you actually go about doing this? You can start off by, let us start off by drawing a diagram, a bunch of circles. Every circle represents a game state. So there are 10 raised to 120 possible game states. Exponentially large number of them. In the beginning, we don't know about any of these game states, whether these are good or bad. Now, each of these states can move into a certain number of other states when you move a coin. I haven't drawn the arrows, but they're going to be arrows from states to other states, right? Now, you play a very large number of games. So, when you play a large number of games, some games you will win, some games you will lose. Each time a board position leads to a victory, I'm going to give that board position a little bit of a green color. Each time it leads to a loss, I'm going to give it a little bit of a red color. So let's say I played this game. I was here, I made the move, it ended up here. My opponent did something, it came here. I made a move, it ended up here. My opponent did something, it came here. I made a move, it came up here. So this is the sequence of moves. And eventually it ended up at a position where I won. So then what I will do is I will find all the moves that I made, and I will color each of these states a little bit of green. But then I can't assign the same green to all of these guys. I know that whatever I did over here almost certainly helped me win. Over here, I'm less certain because there were more choices. I was more dependent on my opponent. By the time I get all the way to the beginning, it's really hard for me to ascertain that it was my board position that was what led to my victory. So what I will do is I will taper the green off. I'll give the brightest green out here, and as I go backward in time, each dot is going to have less and less green. By the time you get to the beginning, it's probably just white, right? Same thing. If I play a game and I lose the game, I'm going to trace my way back, and I'm going to color all of the moves that led to the loss red. Except the further back I go, the less red that I'm going to give it, right? So I'm going to fade the rest with distance. So we keep doing this. You keep playing many, many games. Some you win, some you lose. And basically, you keep adding the dots of color. So if multiple, if from some state you win some games, you lose some games, it's going to get both red and green dots, which means it's going to begin to look somewhat yellow. So as you keep playing, when multiple games visit a state, you're going to average the colors derived from all visits. So some states will get greener, some will get redder. Some that can lead to both victory and loss will become different shades of yellow. And in the early stages of the game, the color is going to be a little more ambiguous than in the late stages of the game. But is that all you can do? You can do more. You can also learn colors from your opponent's moves. If you won, it meant that your opponent lost. If you lost, it meant that your opponent won. So you can go back and use that to assign color. Then you can also learn from other games. You can watch how other people play. And you can say this sequence of moves won, this sequence of moves lost. You can add color. You can go pick up books. You can read books. You can do the same thing. You can learn from experience and keep adding stuff. But then to really, really, really speed up matters, you can play with yourself. Because there's only so much information you can get from books and such like. There's only so much that you can actually speed things up. But a schizophrenic computer can play thousands of games with itself in the same time that it takes for a human being to play a single game. So it can keep continuously playing with itself. And eventually, you're going to get many board positions with different shades of green and red and yellow. And yet, the total number of positions, no matter how long you play, is going to be one teeny fraction of the total number of possible board positions. But from these guys, you have to somehow figure out how to color these remaining board positions. And then once you've colored all of these remaining board positions, now you know. At this point, you are in a good position to actually figure out how best to play the game. So let's say during the game, you find yourself in this game state. That's your current position. What is the best next move? You have two options. You can try to move to the next greenest state, which is the most winning next move. But if you want to play conservatively, you're going to do something else. You're going to say, if I move here, what is the brightest, most red state that my opponent can drag me to? And so you can move, instead of going to the most winning state, it's much better to go to the least losing state. And the least losing state is much more likely to actually win for you than the most winning state. So this is the strategy that all chess games actually use. And at this point, you probably have enough of an idea of how these things are done to actually write a crappy little program yourself, right? So a little alternate terminology. This was a Markov process. It didn't matter how you got to a corner. The future only depended on where you were. Similarly, this too is a Markov process. It doesn't matter how the game arrived at this state. The future depends only on what the current state of the game is. It does not depend on the path to the current state. Right? Questions? Anybody? Okay. So now here's the interesting thing in all of this. It's a very interesting class of problems. If I play a move during the learning process, I do not know whether the move is good or bad until you play all the way to the end of the game. And then you either win or lose. And then you can work your way backwards and decide and get some idea of whether this was a good move or not. So this is Then there are many, many such problems in life, like investment. Is a specific investment plan good or not? You're not going to get an immediate signal about whether it was good or not as soon as you make your investment. You're going to have to wait until something happens in the market, which may be days, weeks, months, or years afterwards. Back in 1995, when I just joined grad school, a friend of mine was trying to unload his Apple shares at $5 a share. I was a grad student. I didn't have the $100 he wanted for the 20 shares he had. In any case, I thought it was a really bad idea because Apple was doomed to failure. It was going to die, right? And well, but if I had actually bought those, I wouldn't have known that it was a winning strategy for another 15 years, right? If I had a time machine, I'd go back and buy them and a few more. Anyway, so here's another situation, like traffic. You're driving, you want to change lanes. Do I change left? Do I change lane left? Do I change lane right? Do I accelerate? Do I brake? All of these may seem to have some benefits, but you won't really know the actual outcome of what you did until long afterwards. Maybe you change lanes and you end up getting stuck in a little traffic jam way down the line. This happens all the time, right? You change lanes and the next lane moves faster. So you change right back and that guy begins to move faster. Happens all the time. So you don't really know till much later whether the actual, whether what you did was good or bad. So in all of these is a common theme. These are control problems where your actions beget rewards. You may win the game, you may make more money, you may get home sooner, but it's not deterministic. There's no guarantee. The world is not predictable. And mostly because the world is playing against you. You're playing chess. There's somebody trying to make you lose. You're driving in the traffic. You're not the only person driving. Others are trying to get home fast too. You're making money. But every time you make money, somebody loses money because it's eventually a zero-sum game. So there's once again, and this environment whose behavior you cannot completely predict. And the worst part of it is that the rewards are belated. You will never know, or almost never know immediately whether what you did was good or bad. And in the face of all of that, you must learn to act rationally and to take the best possible actions. So here's the general cartoon of how this particular world operates. You're an agent. You operate in an environment, and the environment is the game or the market or the road. So you take actions, like you change a lane, you make a move, you invest some money, but your actions change the environment. And the changing the environment can be completely unpredictable. So, and the change in the environment is going to affect your situation. So, but in the process, sometimes the change in the environment will also give you some rewards, maybe immediately, maybe much later. At some point, you get some reward. For the time being, you can imagine that every single action begets a reward, but there is no requirement that this actually happens. The reward may be when the game ends. And now, as far as the agent you is concerned, you have to figure out how best to behave to maximize the total reward that you get over the course of the entire process, the entire game, if you want to think of it as a game, right? So what is the environment experience? From the environment's perspective, the agent took some action, it responded to the action and it changed, and the environment may return some reward to the agent. It gets the person home. The game is won. The stock value goes up. The agent, on the other hand, sees something about the environment, sensor readings, what you see, market readings. There's a lot more going on in the environment, but the agent only gets to see some of this. You cannot really know the entire detail, every detail of what's happening in the stock market. You can only see something about the stock indices and your stock prices. You can see the little bit of the road around you. Maybe you can get some information about what's happening down the road on your smartphone, but you're never going to know everything about who's coming out of where, who's pulling out of what garage, who's going to have a fender bender and stop you for the rest of time, right? So in the face of all of this, the agent observes something about the environment. It takes some actions. It receives rewards. And this is the agent's world. It must make sense of it. Again, the agent's objective is to take the actions that maximize the rewards. So let me formalize this whole problem. This whole thing can be cast as problems of reinforcement learning. There's no supervisor. There's no strong supervision. There's no supervisor. There's only a reward signal, like did you get home sooner? Did you win the game? Did you make money? And there's no one, so which basically means that there's no one telling the agent after every move, hey, that was a good thing. The reward is a scalar. It's just it's a single quantity that you can measure. Like the game was won or lost. That's a 1-0 measure. The time taken to arrive. It took me an hour to get home. It took me 20 minutes to get home. That's a number. I made $1,000. I made no money. I lost the $100 I put into Apple, right? So these are all, again, scalar numbers. And the reward may be delayed. You have to wait all the way to the end of the game, which can take forever. The agent's actions affect its current and future rewards because the agent's actions affect the environment, which affects the behavior of the environment. So this is a complex kind of situation. And yet, we're going to see how we can model this mathematically and how we can make sense of the whole process. It turns out, although it looks so complicated, the whole thing is entirely and amusingly simple. It's very pretty. So here's what we can do. We can think of the environment as a process. And so if you had a mathematical characterization of the environment, this mathematical characterization is going to have parameters which have a true value. That's the true environment. Then the agent must make a model of the environment. The agent is going to model the environment based on what the agent experiences, which may not be anything close to the true story. And based on the closer the agent is to the true story, the more likely the agent is to get things right. But you can't really expect that the agent will have a very accurate model of the environment. And based on what the agent knows of the environment, the agent must formulate a winning strategy based on the model of the environment. So now we can see two things over here. So the agent has a double problem. The agent must know how to formulate a winning strategy. And even if the agent had a perfect knowledge of the environment and how the environment behaves, formulating a winning strategy in this context is hard by itself. If the agent doesn't even know what the environment looks like, but must guess it, that's the second level. If the agent had the ability to formulate winning strategies if it knew the environment perfectly, you still have the problem of actually knowing the environment, and the agent may never know the environment properly. And the two problems actually are combined in the real situation. So let's begin putting some math to it. At each time t, the agent makes an observation of the environment, it receives a reward, and it takes an action. You can change the sequence. It doesn't really matter. I'm just using the standard time indices that's used in the literature. So the agent makes an observation and receives an reward, and based on the observations and the reward that it's obtained, the agent is going to take some actions. Again, remember that the reward might be zero most times, right? The environment receives the agent's actions, and based on the agent's actions, it gives the agent some reward and then changes itself. This changed environment is what the agent is actually going to see. So let's look at what the agent actually looks like. From the agent's perspective, here's what the agent has. The agent makes an observation at time 0, gets a reward at time 0, takes an action at time 0, then makes an observation at time 1, gets a reward, takes an action. This is all the agent gets to see. What did I see? What did I receive? How did I act? What did I see afterwards? What did I receive? How did I act? No matter how you conceptualize the agent, eventually all of the agent's entire experience can be summarized into this little series. So the total history at any time is the sequence of observations, actions, and rewards. So if you look at the history at time t, it's basically this sequence. I did this, I saw this, I got this, I did this, I saw this, I did this, I got this, I did this, that entire sequence. That is the history as far as the agent is concerned. And we need to be able to model this history, HT. We need to be able to model this sequence, the history at any time t, such that based on it, you can get the best, you can choose the best action, and the choice of the best action is the one that tries to maximize the total reward across all time, assuming you're getting a reward at each time, right? Now, from the environment's perspective, the environment receives an action, emits a reward, and changes and produces a new observation. So how do you actually model this? You can model the whole thing. You can define an environment state. So the environment state fully captures the status of the system. Like in an automobile, the position, velocity, and acceleration of the single automobile. In the case of a traffic, the position, velocity, acceleration of every vehicle on the road. That's going to be the environment state, basically the totality of everything that can affect the future. In chess, the state of the board plus who's going to play next, that's going to completely govern what happens in the future. So you can actually define a state for the environment. You may not know what the state is, you may not know the value of the state, but the environment does have a state, right? And so the environment state is what will finally decide the rewards. It may be a complex combination of many things. What we are going to assume is that the environment is dynamic, it keeps changing. And the agent's actions can affect the way in which the environment responds. The environment has a state, the agent may not be able to observe all of it, right? I mean, you see the general setting over here. It's pretty complex, but we're going to still work with it. So now we can define a Markov property. If you define the state of the system properly, then the state of the system can completely specify the future without any reference to the past. But this requires definition of the state, a proper definition of the state. And if you do so, then you will find that the probability distribution of states at future times, given the states at all past times, can simply be compressed to the probability of the state at the next time given the state at the current time. But what do I mean by defining the state properly? For this, let's go back and revisit our old friend, Flight of the Spider, right? So remember, how was Flight of the Spider's process defined? The way we defined the spider's world was the spider lived only on the corners and edges of the room. Whenever he arrived at any corner, he randomly chose, or she randomly chose, one of the three edges to follow. And once she arrived at a new corner, again she used the same mechanism, basically randomly chose one of the three edges to follow to go to another corner. And this was a Markov process. Why was it Markov? Guys? How the spider arrived at any particular state did not depend on how it got there. So how many states would this system have? 8 corners, right? But then Slider has a brother, Glider, who behaves slightly differently. Glider doesn't like to turn back. So when he arrives at a particular corner, he randomly chooses one of the two other edges and only takes one of those two edges. Is Glider Markov?
I think so. I mean, you can model it.
How so?
I mean, you can define a state which you also incorporate a parameter of the last state, or like how it arrives here.
So, anybody see what he's talking about over here? In the first case, we had eight states, and so from each state, you had a probability of 1/3 of going off to the three adjacent states. And in the first case, in the case of Flight of the Spider, we defined the corners of the states, of the cube as the states. But now, in the case of a brother, I can think of, so let me number my corners as 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 corners over here. And then I can define my states as edges with the direction, which incorporate the direction of travel. So my states are now going to be 1, 2, which means that the spider has gone from corner 1 to corner 2. It's going to be 2, 3. Does it? No, there's no 2, 3. There's 2, 4, right? There's 2, 8. And then I can also have 2, 1. And then I can have 1, 2, 1, what was this number? 1, 2, this must be 3, right? 1, 3, and 1, 5. So you see what I'm doing over here. I'm actually thinking of the entire edge along with the direction of travel as a state. And so if the spider has traveled from corner 1 to corner 2, then the only other possibilities are edges where it goes from corner 2 to some other state. So the 2 transitions possible are going to be these guys, and each of them has a probability of half. Right? So I can actually draw the entire Markov chain in this manner, and now this Markov chain is going to have 24 states, where every state has an outgoing edge of two possible outgoing edges, each with a probability of half. Now suppose they have a cousin who decides based on the past 2 edges where he's going to go. Would that be Markov? That's also going to be Markov, because now I can think of pairs of edges as forming my state. And in that case, now I'm going to have, how many states would I have? Many more, 24 times whatever, right? Hundreds of states. But still, it's still a Markov process. So what this means is that I can just group my past more and more. And as the process becomes more and more, begins to refer more and more to what happened in the history, what happened in the past in terms of time, I can redefine my state as something that includes everything that must be considered in deciding the future. And now the whole process is still Markov. So in that sense, any causal system can be viewed as Markov with an appropriately defined state. So the Markov state is going to be different from the apparent state. So here, for example, the Markov state was an edge. The apparent state is a corner. So the apparent state is what you see. The Markov state may be everything that actually, the sequence of, the combination of the sequence of apparent states that actually led to the current situation, right? And so once you define this Markov state in this manner, then I can always say that if I think of the Markov state as maybe the sequence of all apparent states until the current time, then every system eventually becomes just Markov. The probability of the Markov state at time t plus 1 given all Markov states until now is simply the probability of the Markov state at time t plus 1 given the current Markov state, right? So, unless of course this goes all the way to infinity, if it's dependent on the infinite past, then you get into mathematical niceties we don't want to deal with. But anyway, so I can kind of model the true environment as Markov, where the future depends only on its present. And to be able to maximize his reward, the agent must ideally know all about the environment state and all of its dynamics. The problem is the agent can't know all of this. The agent must model the environment process. Basically, the agent must formulate its own model for the environment, which ideally must match the true values as closely as possible, but this must be done based only on what the agent observes. So here's what the agent side of the story is going to be. The agent has an internal representation of the environment, which may not match the true one at all, and may be defined in any manner. And so formally, the way the agent is going to define the state is going to be dependent on the history that the agent has observed. So the agent state is some function of the history. It's the agent's model of the environment, which may be different from how the model environment actually behaves. And the gap between the two is going to lead to suboptimality in the agent's choices. Now, so to see the distinction between the agent state and the true environment state, let's look at the simple example which I stole from David Silva's slides. So let's say you have a mouse, and in the first experiment, he sees a light goes on, he sees a light goes on, he presses a lever, he hears a bell, he gets an electric shock. Right. In the next one, he hears a bell, sees a light goes on, presses a lever, he gets a piece of cheese. Then the next one, he presses the lever, he sees a light go on, presses the lever again, he hears a bell. Should he be expecting a cheese, or is he going to get zapped? Right? What would your best guess be? Anyone? Why?
Because we've only seen that ending pattern once. The lever bell.
The lever bell once. Okay?
I mean, yeah, it matches almost the first one.
But maybe you can say you push the lever twice, you get a cheese.
If you push the lever twice, you get a cheese. Right? So the whole point is there is no unique answer, right? This is the agent's model, the rat's model of the world. And to really know the actual state depends on everything that happened all the way till there, right? The environment's behavior is unknown. The rat has to come up with its own model, and if it comes up with the wrong model, it's going to get zapped, right? So you get the idea. You see the distinction between the environment state and the agent's model of the environment state. The two can be different, and the difference between the two can be fatal, especially to rats, right? So different definitions of the state result in different predictions, and the true environment state is not really known. If you knew it, your predictions are going to be much more, much better, right? So yes.
So what's the example of a perfect environment state for this? We just don't know what actually causes the cheese to appear, and so that's...
So the agent has some internal rationale based on some current set of variables, which you may not be exposed to. That is the environment state, right? Think of this environment as this gigantic or maybe even small program. In fact, the agent may not even be referring, the environment may not even be referring to any of these guys, and might just be flipping a coin, right? So the environment state is unknown. You are modeling this, and in fact, you can be completely off. Yeah? So the environment state is Markov, an assumption that's generally valid for properly defined true environment state. In theory, the agent doesn't observe the environment and environment's internals. The agent may be able to observe the outcomes, so that there's a difference between the internal state, as we saw, and the apparent state, which is what you actually observe. And that is something the agent can observe. But the mathematical fact is just by observing getting the sequence of observations, that does not provide any reason for the agent to believe that the environment is actually Markov. So even if the environment really is, we won't get into the details of that. But the practicality of it is that the agent is assuming stuff in order to model the environment, and the agent can assume anything, right? So here's what we've got. There's another aspect that comes into this whole problem, which is observability. The agent's observations tell it about the environment state. So in this case, if it's got a chessboard, it sees everything about the chessboard. So the agent actually sees the entire environment state. Now, knowing the environment state is not enough. You also need to know how the environment behaves, the transitions. So just being able to observe the environment state still leaves the agent insufficiently informed about the environment, because the agent has to know how the environment transitions from one state to the other. It's like knowing this room has 8 corners, but not knowing what rules the spider uses to go to different corners. So if the agent can observe the entire environment state, now that means the agent's notion of the environment state is isomorphic to the actual environment state, but it's not the same as knowing everything about the system. So this is the kind of situation. In this situation, we will call this whole thing a Markov decision process, where the agent takes decisions, but the agent knows everything about the states, but not about anything else about the process, how the environment actually switches between states. Now, you can have a somewhat more realistic version of it. So you can think of a poker game or real life or the stock market, where you only see some stock prices or you only see the traffic immediately in front of you. In this case, you don't even observe the environment state fully. And so this means it's a partially observable process. And so these are what we will call partially observable Markov decision processes. It turns out that if you learn all about Markov decision processes, you can transpose much of what you know to partial POM-DPs. So we're going to focus on MDPs rather than POM-DPs, right? So here's the world as we know it. You have where the spider can go to next only depends on where the spider is currently at. So this is which means that the definition, this sort of is an example of the Markov property. The state of the system has a Markov property if the future only depends on the present. So the spider is still stochastic. The future is not deterministic. But the 3 states it can arrive at and the probabilities of the 3 states depend on the spider's current state. So the future depends on the present, even though it is stochastic. And states, as we saw, can be defined to have this property. So that brings us to our first mathematical definition, which is a Markov process. A Markov process is a random process where the future is determined only by the present. It's memoryless. It's fully defined by the set of states and the state transition probabilities. Again, keep in mind that we have to define the states carefully. So formally, you can say a Markov process is defined by this tuple, which includes the set of states and the transition probabilities, where the set of states is a possibly finite number of states. The transition probability is a full, complete set of transition probabilities. And when I write P of S given S prime, I'm really saying P of the state at time t plus 1 equals S, given state at time t is S prime. Yes?
I have a question about the Markov property. So in that example, you said if the future actually depends on the past, then we can just model the process in a way so that it is Markov process, right? So can you give an example where the process is not actually Markov?
If you have to go all the way back to infinity at that point, right? Anytime you have a finite horizon, we can always make a Markov process of it. Yeah.
Convert that into.
Yeah.
Thank you.
Right. So, but if we can imagine validly that there's a finite horizon, however deep, it ends up being Markov.
So if it's finite, then we can always model.
Yeah. So for processes with discrete finite set of states, you can actually write this transition probability as a matrix. For continuous state processes like the state of an automobile, you actually end up writing it as a function. The probability of going to a state S prime, given that you're currently in some state S, is some function of S. So you can just write it as a function, right? So in the case of this guy, how many states would it have for flight of the spider? We have 8, right? But what would the transition probability matrix be? No. So here, the transition probability matrix is we have 8 states. If I use that numbering, then I can go from, if I'm in 1, I never go back to 1, so a 1-to-1 transition is 0, right? If I'm in 1, I can go to 2 with a probability 1/3. I can go to 3 with a probability 1/3. I can go to 4, I cannot go to 4. I can go to 5 with a probability 1/3. I cannot go to 6, 7, or 8, right? If I'm in 2, I can go to 1 with a probability 1/3. I don't go back to 2. I cannot go from 2 to 3. From 2 to 4, it's probability of 1/3. Then from 2 to 8, it's a probability of 1/3. So you see exactly what the transition matrix is going to look like in this case, right? For each state, I would be writing down the transition probabilities of the transitions to the various other states, including itself, as a row, and the collection of those are going to form a transition probability matrix. So having this matrix and the definition of states completely specifies the Markov process. Now, if the spider doesn't like to turn back, this is glider, this too is a Markov process. What would how large would the transition matrix over here be? 24 cross 24. And each row is going to have how many entries? Non-zero entries? Only 2, right? And each of them is going to be half, the way we defined it, right? So you see it's fairly easy, straightforward. Now, which takes us now on to the next step. We've sort of defined a Markov process, we've defined glider the spider, and we've defined our setting for learning. But let's try to, a simple Markov process doesn't completely define the world, because the way we define the process, the agent gets rewards, right? So we have to introduce the notion of reward. So we'll take the next step and define something called a Markov reward process, which is just a Markov process but with rewards. It's a Markov process where states give you rewards. Anytime you arrive at a state, you obtain a reward R drawn from a distribution, where the distribution is state specific. So you can think of something like this. You have the corners, you have the room, and you have swarms of flies at each corner. And anytime Flider the spider arrives at any corner, he nabs a fly or a mosquito or whatever happens to be swarming at that corner. Now the rewards are corner specific because you don't have the same swarm of the same size of insects at every corner. In any realistic room, you would find that insects prefer some corners to others. So this means that the probability distribution of the reward changes with the state, right? So Flider, the spider, with this set of rewards is a Markov reward process. What about this one? Is this a Markov reward process?
Yes.
How?
Allow zeros, 1.
There are no rewards at seven of the states, and there's a reward of 1 at one state, but it's still a Markov reward process, right? You're giving it a reward. So formally, a Markov reward process is a tuple which includes states, transition probabilities, rewards, where the reward function is the set of reward distributions for each state, and there's this peculiar thing called a gamma, which is a discount factor, and this is where we actually factor in the real world. So what does a gamma as a discount factor really mean? What on earth is this guy? So think of, let's hold spider the flider off for a moment, right? So think of what happened when we were trying to tag states when we were playing the chess game. When we were playing the chess game, when you won the game, you looked back and then you didn't assign a causationness of 1 to every past state that you had visited. You didn't give them all the same green color, right? As it went further and further into the past, you were less and less sure that that guy was the reason you won. So as you went into the past, you tapered the color off. Remember? That's the way we defined it. So in other words, if you think of what you gained as you went backward, what you assigned rationale to, or what you assigned causation to, as you went backward, you assign it less and less. You can do the same in the reverse. So let's say I go through the process and I get some rewards. So if I'm standing at the current time, I run an experiment, I go through several steps, I keep getting rewards through the steps. Then if I want to think of that as, if I want to use my first experience as an indicator of what will happen from the same state the next time around? Am I going to assume that everything that happened in the future is equally important? Am I going to assume that the fact that I caught a big fat fly 1,000 steps from now to be really important, say this is what I must go take this direction for? You're not going to do that because it's so far in the future, it's very uncertain. On the other hand, something that happened immediately in the next step, the last time you ran the experiment, you're going to give that a lot more importance. So if you want to think of repeatability of these experiments, if you run one experiment and use that as an indicator of how you must behave in the next experiment, you're going to give a lot less importance to the far future than you're going to give to anything that happens in the next step, right? So this is what we mean by discounting. As you have a discount factor, except the discount factor we're going to use is something exponential. So let's say you have a one-step expected reward. There's a difference between an expected reward and the actual reward. What is the expected reward? The expected reward is going to be the mean of the distribution over here, right? So let's say you have an expected reward from a one-step expected reward of R1, right? So in this case, there's no corner over here. There's no edge over here. So is the one-step expected reward going to be greater for coming here or going here? These flies are far fatter, but there are fewer of them, right? So, but yeah. Note that the distinction between the expected reward and the sample reward. Sample reward is what we actually get. I'm going to represent it using a small r. The expected reward is what we may expect to get. I'm representing it with a large R, right? And in this case, if I want to think of the one-step reward, I just say that I'm going to get some reward if I go here. I'm going to get something else if I go here. And this guy, I have much greater expectation of getting a reward over here because even though the flies are smaller, there are many more of them. Here, you may just not catch any, even though they are larger, right? But then suppose I think of going out into the distant future, not just the one-step reward, but the reward all the way into the future, right? In that case, given a choice between going to 2 and 3, which one should the fly go to, spider go to? 3, because it gets much closer to this massive,
But if you go to 2, if you go all the way around, you're supposed to be getting more rewards.
If you go to 2, eventually maybe it keeps staying there, right? So if it goes here, it can go back and come back, go back and come back. The point is this, that the gain from here is greater than the gain from here. In the best case, the gain from here is 2 steps away from the gain from here, right? So if you're here in one step, you can get into this juicy bunch and begin grabbing flies and stay there. So anything that happens from here it's going to be more delayed. So the total reward going all the way into the future is always going to be lesser if you go to 2 than if you go to 3. Right? So anything that happens from 3, I'll have to get to 3 before I get to 4, even if I go to 2. And in the process of getting to 3 from 2, I'm going to be making fewer rewards than I would if I were originally directly at 3. So in this case, if I were looking all the way into the future, the place I really want to go to is 3, not 2. Right? So you see the distinction between an immediate reward where you want to go to 2 and the reward in all the way into the future where you want to go to 3. Except, so the long-term reward may be expected to be better if the spider goes to 3, but can you be sure? You really can't be sure, right? Just based on this thing, it seems to me it should be a better choice to go to 3, but you really want to be a little less certain. So here's what you can say, that I ran an experiment, since I can't really be certain, and in one experiment I go to 2 and then follow whatever chain. And I keep repeating this experiment, right? Now, the sequence of rewards that I got some reward at t plus 1, and then I got some reward at t plus 2, and I got some reward at t plus 3, but I'm going to assign less importance to the reward at t plus 2, even less importance to the reward at t plus 3, because the future is less certain, right? And so over repeated experiments, if I were to decide as the spider whether I must go to 2 or 3, and I ran an entire bunch of simulations, I'm going to give lesser and lesser weight to things that happen into the future. And so the total return that I'm going to get in any particular experiment is going to be the weighted combination of all the rewards that I got in that particular experiment. So this weighted combination is going to be the reward I got in the first step plus gamma times the reward I got 2 steps from now plus gamma squared times the reward I got 3 steps from now, and so on. So this is the weight, this is the return. There's a distinction between the return and the reward. The reward is something that you get immediately. The return is what you get if you follow the process all the way to the end, but with discounting. That's your expectation of what you would get, or that's some value that you assign to what you're going to get if you keep following the process all the way to the end. Yeah.
So I wonder if the agent actually really see all the way to the end, because there's so many possibilities, and I guess there's a lot of computation.
So no, you're going to just think of this as a sample, right? As a draw, a simple draw, right? Many possibilities. We'll take a look at a nice example, right? So anyway, I'll get to that. So this discount factor gamma is our belief in the predictability of the future, that what you encounter in one experience is indicative of what you're going to encounter in the next experience of the same process, right? So the less you think it's indicative, the lower the gamma is going to be. So if you say gamma equals 0, then the future is totally unpredictable. Although I can see what happens in the next step, what happens next is something I have no faith in at all. If I say gamma is 1, I say that this experience I had once is completely indicative of what is going to happen every single time. And in reality, you want to live somewhere in between, but not always. So first, let's look at our distinction between rewards and returns. So let's say our spider goes wandering, and these are all the spiders, all the flies it got. It got a fly of size 1, size 2, 0.7, then eventually it overate and died. And so now, so are these sample rewards or expected rewards? Sample rewards. This is one experiment, right? Now, what are the expected rewards? You have no way of knowing. You need to know the distribution. Just a single sample is not going to tell you anything unless the probability distribution is a delta. You have only one fly at each corner, right? So, and you have only one way to go through the whole process. So you need to be, unless the entire process is deterministic, it's always going to be a sample reward, right? Now, let's say I use a discounting factor of 1. What is the return at time t equals 1? It's just going to be the summation of all of these things which made him die, right? But suppose I use what is the return at t equals 7? That's going to be these 3, right? Everything that happens in the future from t equals 7, sum of all of those rewards. Now these are all sample returns, right? Because it's a single sample that you're computing things over. It's not an expectation, right? These are all sample rewards and sample returns. And now, what is the return at time t equals 2 with a discount factor of 0.5? It's going to be 2 plus 0.5 times 0.7 plus 0.25 times 1.2 plus 0.125 times 0.5 plus 0.0625 times 3, right? Each time you're going to be halving, and then that's what you'll be adding, right? So discounted sample returns by themselves are kind of a fuzzy meaning. If you've already observed it, why do you want to discount it? It only makes sense if you think of these as samples in one experiment that you want to use as indicators of what will happen in the future, right? So now let's go back to this case. This spider gains a reward of value 1 if she consumes the fly, and there's no cost for walking, right? What is the value of starting at each corner? So what do I mean by this guy, right? If I'm over here, if the spider keeps walking, what is the eventual return going to be? 1. if I'm over here? Because the spider is going to keep walking and eventually it's going to get the fly, right? So in this case, the expected return from any corner is 1.
But that is assuming discount factor is 1.
Pardon me?
Discount factor of 1.
Yeah.
So the discount, yes and no, right? Eventually she's always going to get the fly in this particular case. It doesn't matter how much you discount it, eventually she's always going to get the fly, right? So in that sense, if the fact that there are no costs and there's only one reward, now that discount factor will actually begin to matter if I change the things a little bit. The value of being at any corner is going to be 1 because eventually she's deterministically going to get the fly, right? But then let me do this other thing. So the value of a state is the expected total discounted return when the process begins in that state. And because it's Markov, you don't really need a time indicator. It's the expected value of g given the state, right? Now, let me give you a slightly different version of the same problem. The spider is hungry, and the spider loses energy when it walks one edge, right? So she gains a negative reward of -1 every time she goes from one corner to the other because she's losing energy, right? And then she gets a positive reward of 1 if she gets here. Now, what is the expected return if she starts at C1?
Minus something.
So there's a total reward penalty associated with each corner. -1 if the corner has no fly. So 1 if the corner has the fly. So the reward is -1 for C1 through C7 and 1 through C8, right? Exactly as we defined it. Now, we could also assign things different costs to different edges, which is being simple, all right? But then, what is the value of each corner now? What is the expected return as opposed to the expected reward? The return is, if you follow the process all the way to the end, what is the return that you're going to get for each corner? Again, the return is the rewards, the discounted sum of rewards into the future. And the reward is what you get right now, right? So how would you actually compute this? What is the value for each corner in this case, assuming a discount factor of 1?
Solve the linear system we had before.
Exactly, right? So if you're over here, so let's say you're over here, right? At this point, over here, the value of being in the state is 1. Over here, the value of being in the state is, with a probability of 1/3, you're going to lose energy 1, and then you're going to eat the fly, right? With a probability of 1/3, you're going to lose energy 1, and then you're going to have whatever value you have over here. With a probability of 1/3, you're going to lose energy 1 to go here, and then you're going to have whatever value you have over here. So the value at any state is going to be -1, which is the cost of going to the next corner, plus 1/3 times the value of 1/3 times the value of C2 plus 1/3 times the value of C3 plus 1/3 times the value of C4. This is exactly the same equation we saw in the beginning of the class, right? It's exactly the same thing, assuming a discount factor of 1, gamma is 1. And so now I can solve these. I'm going to have one such equation for each of my 8 corners. And now I can solve these equations to compute the value for every single corner. Does that make sense to everybody? Right? And so, but let's say I have, instead of just this one fly, which is not going, which is just sitting there, which I'm eventually going to get to anyway, right? Now I have to begin worrying about discount factors and such like, because there's a cost. There are negative costs and positive costs, right? Now, let's say I have this setting. There are flies at every corner. The expected reward after arriving at any corner is some RCX, where CX is the corner, which is the average size of the fly minus the travel penalty. And let's say immediate rewards matter, because you're a spider, right? You're looking for instant gratification. So in that case, gamma is less than 1, right? So in this case, I can say what is the value of being in each state? It's going to be exactly the same equation. The value of being in state 1 is the reward of state 1 plus gamma times the expected reward from the next state, whatever the state is. The value of state 2 is the reward of state 2 plus gamma times the expected reward from the next state, right? Or the value from the next state. So basically, if I'm over here, the value of being over here is whatever reward I'm going to have over here, plus 1/3 this value, plus 1/3 this value, plus 1/3 this value. Because the value actually considers, basically I'm saying this, the value over here is the discounted sum of rewards all the way to the infinite future, right? Which is the same as saying this reward plus the discounted sum of rewards from here all the way into the infinite future. Plus, 1/3 times the discounted rewards from here all the way into the infinite future. Yeah.
So you're assuming that when the spider eats a fly, there's going to be a new swarm of flies. It's not that you eat it, then it's gone.
Yeah. So it's a distribution. There are flies. Yeah.
Okay.
Right. And it's an infinite swarm of flies.
But you're saying it's kind of recurrent.
Yeah.
Like basically when you look at the
I can actually model the fact that if I eat a fly, the fly goes away. But right now we're going to say if it eats a fly, some other fly comes and replaces it, right? Which is fine. We don't need to make the model too complex, right? But then, this is a familiar equation. This is exactly what we've seen. And if gamma is 1, we saw it's the same as the previous example, right? In fact, so this equation is what we'll call the Bellman equation. The Bellman equation is the value of a state which is the expected discounted return not reward. The return is the total discounted reward into the infinite future, right? And reward is the immediate reward. So you say that the value to each state you can define a value function which is the expected discounted return when the process begins at that state, right? So it's going to be so I can say the return is the discounted rewards starting from that time. The expectation of this guy for each state is the value assigned to the state. And the Bellman equations that we just saw is that the value assigned to any state is going to be the reward of that state plus gamma times the expected values of the states at the next after one transition, which is you take a weighted combination of the values of all the states you can arrive at, where the weighting factor is the transition probability to the state, right? So again, these are very simple equations, nothing particularly complicated. And this is the basis of pretty much all of reinforcement learning, right? Everybody get what I'm talking about? Right. So why discounted return? Now discounted return has got two interpretations. One is that you want to trust the future less and less and less, right? But what happens if I say I trust a single sample, every sample perfectly? Then what is the actual return going to be? If the rewards are all positive, the return for every state is going to be infinity, right? So you need this discounting factor for two reasons. First is that you really do not want to assign too much importance to something that you saw in the distant future in any particular run, right? Because it's not indicative of this. As you go further and further out, you have more and more variation, right? But there's also the second factor that if you think of the spider and the fly clays, and now this goes back to your problem, what is the value of so this goes back to this situation here, right? What happens if after eating the fly, another fly comes there? What is the value of each state? Infinite, right? Because the spider is going to die of overeating, unless there's a cost associated with each edge. If there's no cost for walking, the spider wanders around, grabs a fly, wanders around, grabs a fly, wanders around, grabs a fly, and belly bursts and dies, right? So you want it to work the fly off. You want a cost. So that's why when you have a perfect replacement process of this kind, assuming that there's no cost, and assuming that there is probably a horrible thing to be doing in the first place. Secondly, once you begin assigning a cost, you have to worry about not letting run things forever, right? So if all of my gains are positive, if my discounting factors, if I didn't have a discounting factor, I'm going to have a net reward or a net return of infinity from every state, unless I have a finite horizon process, which is like the case of the fly where the spider eats the fly and the game is over, right? In that case, the horizon is finite. When the horizon is finite, a discount factor of less than 1 doesn't make a whole lot of sense, because you can see all the way to the horizon in each single run, and you can trust what happens in the far distant future quite a whole lot. But if the horizon is infinite, mathematically speaking, you cannot have a discount factor of 1, things are going to break down. So you really want a discounting factor which makes sure that the return that you compute from any state is finite. And it doesn't have to be exponential. It can be something that tapers off with time. How much I trust the reward I got at the next instant has got to be greater than how much I trust the reward I get 2 instants from now, which in turn has to be greater than how much I trust rewards I get 3 instants from now. My faith in my sample has to go down with time. It doesn't necessarily have to go down exponentially. We just have to make sure that the sum of all the rewards that I got in any particular infinite run ends up being finite, right? It just turns out that this exponential weighting is mathematically the most convenient. Right? So I can write the Bellman equation in this manner. I can actually write the whole thing as a matrix. So these are the values for all of my states. These are the expected rewards for arriving at that state. This is my discount factor, this is my transition matrix, and these are the values for all of the states. So my set of each of these equations is going to form one row of this matrix equation, right? And so I can write, if I represent this vector as this curly v, this expected reward from each of the states as this curly r, and the transition matrix as this curly p, then I can say v equals r times gamma pv, or solving for it, I can just, given the Markov process, random process, I can actually compute the values for all the states in one fell swoop, yes.
So the Bellman expectation equation only looks at the current reward and the next step, right?
Yeah.
So what about if the discounting factor gamma is large? Then should we look into further steps?
So these are expectations, it doesn't matter. This equation is perfectly complete. It's right. Think of it this way: the discount factor is, so the rewards that I get, the return I get is the current reward plus the infinite future, which is the current reward plus the discounted next reward and the infinite future. It gets included in, right? Because this guy is the return, not the reward, right? And so you can actually solve this cleanly, mathematically, right? So finding the values of states is a key problem in planning and reinforcement learning, but the only problem is if the number of states is very large, this transition matrix is going to be enormous. You're not going to be able to invert this matrix. You're not going to be able to solve this equation. And in fact, pretty much all of RL is all about how to tackle this problem more than anything else. So I'll stop right here. We haven't even talked about Markov decision processes, but it was important to get the notion of the Markov process and the reward process understood before we begin to consider the fact that your actions can change the world. And we'll see that in the next class. Thank you.